Okay, so my name is Andrée Monette. I'm currently a data analyst at Energy Hub, which is a smart thermostat company in Brooklyn. And I'm giving a talk on garbage collection in CPython. So why a talk on garbage collection in CPython? Well, you know, we're in New York, and I live in... So here we can see this is a picture of Brooklyn. Here's the borough in which I live and work. And so, you know, it'd be nice to have like some garbage collection, and if Python could do something about it. But no, really. Okay, so the reason that I want to do a talk in garbage collection in CPython is that about 1.5 years ago, Tom Ballinger, who's a facilitator at the Reeker Center, was basically holding like a little mini workshop on Python's magic methods. And so I went to this little mini workshop, and so we were learning about various things like when you use like dunder stir versus dunder repr, when init gets called, when new gets called. And so after this, I was looking through the documentation, and I come across this. So this is the documentation for dunder del, which is the finalizer. And I'm not really expecting everybody to be able to read this necessarily, but you see how the actual documentation is 4 lines long here. There's a note on it, which is 10 lines long. And then there's, in like bright red, outlining this box, there's a warning, which is like 8 lines long. So the warnings in the notes take up like something like 85% of the documentation for this thing. And all the other magic methods, they're just like, a few lines, okay, like stir gets called when you call the built-in function stir on this like object or whatever. So I was like, what's this del thing? And more importantly, how can I break it? How can I just like do completely like nutty things? If it's got so many warnings with it, the thing you want to do with like something that's like covered in warning labels is just like, how can you just like completely mess this thing up? So in order to figure out how to do that, we first have to learn like what it's doing just in a basic sense. So del is implemented as part of like Python's memory management system, and what that system is designed to do is collect garbage. So what's garbage, first of all? So garbage is basically any object that will never be used again. And if we had some sort of magical way of detecting like what objects will never get used in the program, then we could use that to solve the halting problem, and then that's literally impossible. So we need to use like a more pared down algorithm than just like some sort of magic. So programming languages have constraints on what you can do. And so one way you can ensure that an object will never be used again is if you can't access it from anywhere. So we can just designate that as garbage. And so what does garbage collection want to do? So like once we have our garbage, we want to reclaim the resources that they're using. And usually this is memory. Sometimes they have files open, and we want to make sure those are closed. Sometimes they have a network connection open that we want to close. And in programming languages generally, there's 2 main ways of doing this. First is that you take a root object. So in Java, this would be something like main. And then you go out from there, and then everything that you can't get to, you collect. And you run this every so often. But Python mostly uses what's called reference counting. So you keep a reference count on every object. And whenever you create a reference, you increment it by 1. And whenever some reference becomes unreachable, you decrement it by 1. And then as soon as a reference count of any object hits 0, you just collect it. And so there's a del keyword. And unlike, say, stir or repr, del doesn't actually call dunder del. What del does is it removes whatever name is being, so if you say like del A, then it'll remove the A name binding from the namespace, and then decrement the reference counter by 1. And so you can get into a problem with this where you have what's called a reference cycle. So you have like some object A that has, it's a container or it's like some user-defined object, and it has a reference to some object B. And then object B has a reference to object A. And no matter what happens to the other objects, even if you like have no ways to get to these from the global namespace, they'll always have like one reference to each other. So the reference count is never going to get 0, and normally these objects aren't going to get collected. So del, which we're looking at before, is what's called Python's finalizer. So this is a bit of code, somewhat like a callback, that gets called whenever an object is about to be destroyed. And an interesting thing about this is just a method on the class definition, and it still has access to the object. And in fact, del has a guarantee that all of the sub-objects will not be destroyed. So it always destroys like the top level object first, and then like cascades down, and then destroys any sub-objects that are available. So a thing that we can do here, so we can actually put a reference back and prevent the object from being destroyed. So this is what I'm calling a zombie object. So when the zombie object gets destroyed, we have it say brains, right, because it's a zombie. And then it just comes back. So it creates a global reference to itself. And what this does is this increments the reference counter by 1. And then when it gets to the end of del and goes to actually finally destroy the object, it actually doesn't get destroyed because the reference count is 1. So I can do this as a so this was that piece of code that we just ran. And you can see that even if we like continue to delete the zombie object, it just keeps on coming back. And if we look at the ID of this object, we can see that even if we try to run the finalizer on it, it's actually the same object. Like the object was never destroyed in any of this. We can, like no matter how many times we call del, it's not going to go away. And let's exit. And, sorry? If you set zombie to none, so if you set zombie to none, then that's another way of like trying to destroy it. So we can, I guess, quickly. So you wanted to set it to none instead of destroying it. And notice when you actually exit out of the interpreter, it tries to destroy it. It ends up getting like 2 last cracks at you before it finally dies for good. So del. So you might think that you wanted to use del to, for example, close some file descriptor or close some socket that you had open because, okay, so the object's being destroyed. Let's close its resources. Well, it turns out that there's no guarantee that del is going to get called exactly once. So if for some reason, like you have a caching layer or something that like creates another reference, your del can get called as many times as like it wants, basically. And you can end up in a situation where you try to close some socket twice or close some file twice, and then you get exceptions. So the more Pythonic way of doing this, and I'm sure like probably most people have like seen this, is like you want to use a context manager and make resource like clearing explicit. So we will have like something like with open file name is f, and then the file object has like a dunder enter method and dunder exit method, and you're making it very explicit about, I want this resource to be like claimed at this particular time. All right. Right, so there's a few ways of adding references. So there's the obvious, like we assign it to a variable, either local or global. There's putting it inside a container. There's assigning it as an attribute. And then there's like weirder examples. So if you try to do live demos of this reference counting scheme in a REPL, so the basic Python REPL stores a reference to the last expression value in the underscore variable. So you'll end up having like a situation where you do, you create something that has a dunder-del method, and that doesn't actually get called until you like type like 2 or a into the REPL, because that overwrites the value in underscore, causing like the reference count to finally drop to 0, and then like you have some code that like executes later. And if you try to do this in IPython, you're kind of hosed, because like there's a dict that stores all of the return values of all the expressions. So when you create an object, you end up creating 3 references to it, and one of them is not going away. So you don't actually like see this garbage collector reference counting scheme work at all. So del is one of the ways to get rid of a reference. There's also overwriting a reference, as we saw. And there's also if it passes out of scope of a function. So what's another way to break this? So I thought, OK, how about we make what is essentially a fork bomb? So this is a Lernian hydra. So it's named after the mythical beast, the hydra, which when it had its head cut off, it would grow 2 heads in its place. So this is an object that when it's deleted, it creates 2 new instance objects in its place. And so you'd expect, just from a look at this, that you would just always like create the left head, and then like when that head got deleted, it would just like create a new left head, and it would just loop forever and just go entirely in one direction and never stop. So we can try it. All right. So as you can see, we get something very odd. So it does do this kind of like tree thing where it's essentially doing a depth first search. But this depth first search has a maximum depth of 50. So you might be thinking, like, why is it 50? Well, it turns out that, again, this is an idiosyncrasy of like CPython's garbage collector. I was stumped about this for a while until somebody suggested, why don't you search through the CPython source code for the constant 50? And it turns out that the constant 50 only appears a few times in the source code. So I found it pretty quickly, and it's the pytrash unwind level in object.h. So what happens is if you have a call stack, which is deeper than 50, in order to avoid a cascading bug when you allocate containers and you lead to this endless like series of allocations, there's a constant defined in CPython so that it waits for the call stack to unwind to below 50 calls before doing garbage collection again. So it will stick anything that has a call stack of greater than 50 onto this stack and just keep on going from there. And this is, of course, like this like forking program never actually got below 50 for any like reasonable length of time. It would always put like a 51st object on there. And what that eventually did is made my process run out of memory. I would be fine, actually, if I had on the order of 2 to the 51 bytes of RAM. But since that would be like several planets worth, unfortunately, like this constant means that you know, the fork bomb is going to like run out eventually of memory. So we can't even like rely on del being called at a predictable time. So I decided to take this a bit further. This is a chessboard with 8 queens on it. And so we've got something like, kind of like a depth first search in that last example. So what I decided to do is actually make a depth first search like algorithm solver in the Finalizar. And so basically it's a class, and each object is a chessboard, and when it's being destroyed, it creates 8 more chessboards if it's a valid position. And eventually it like trickles all the way down through to the bottom layer. And then as things get cleaned up, as they are valid or invalid, like 8 queens positions, it eventually goes all the way back up to the top layer where it tells me the answer. So I'll just show this. Oops, sorry. Right, so so right now, it hasn't done anything. There's just a class definition and an infinite loop. So I'm going to Control-C out of this. And at that point, the destructor like begins. And it creates all of its tree and traverses all of the board states. And there are 92 solutions to this problem. Right, so I think some people will have heard of the global interpreter lock. So the global interpreter lock is this thing that exists in CPython and PyPy, where you can only have at most one interpreter manipulate Python objects per process. And the reason this exists is because garbage collection isn't thread safe. But more specifically, handling reference counts. So this whole thing of incrementing and decrementing reference counts isn't atomic between threads. So what this means is that you could have one thread like try to set the reference count to 2. So like, let's say it's getting rid of a reference, and it's like the reference count is currently 3. Let's set it to 2. And then another thread tries to get rid of a reference. It's like, oh, it's currently 3. Let's set it to 2. So they both set it to 2, and then suddenly your reference counts are off. And if your reference counts get to 0 prematurely, then you get segmentation faults because it tries to like clear out the area of memory that the object was using, and then you try to reference it again, and like this is a serious bug. So this is why the global interpreter lock became originally a part of Python. And I know, like personally, the global interpreter lock has been a little bit of a headache for me, like doing parallelization of like certain things. So you know, if you're wondering why it's there, this is why. And there, yep. Yeah, I think Ruby is like, it's basically the same reason. And the reason that they don't have a global interpreter lock in IronPython or Jython is because those interpretations, like they just use the garbage collection mechanisms of the runtimes that they're based on. So like Jython uses Java's garbage collection. So reference counting is almost the whole story, but there's an important other mechanism at play, and it's called cycle detection. So cycle detection, so remember how I said earlier how you could have an object A that has a reference to an object B, and then an object B that has an object to a reference A. You might think, like, when would I ever do that? But actually, that comes up a lot in practice. So if you're parsing like some DOM or something like that, then you have objects that have references to their parent objects, and the parent objects have references to their child objects. So this is going to come up like actually reasonably often, that your reference count is never going to get to 0, even if you remove all like references from the global namespace. So what CPython does is it keeps track of all of the objects that could potentially be a problem. So it doesn't do this for atomic types. So your strings and your ints like are not tracked. It does track user-defined classes, and usually it tracks containers. But there's an optimization where it doesn't track containers that contain only atomic types. So if you have a list of like A and B and C, it's not going to track that. And you can tell actually whether any object is tracked by importing GC from the standard library and then calling the isTrack function on it. So it's got a cycle detection algorithm. It runs rarely, and the default is that every 700 times you have an allocation, it will do a run of the cycle detection. Sometimes they'll do it manually. You can do it manually with gc.collect, and it's generational. So let me show what I mean by this. So this is the current memory usage of this process, as 4,948 kilobytes, I believe. And I decided to make so I made a huge object. So this is a self-referential huge object. And my memory usage went up to 493,000. I decided to allocate 0 objects, so we're not going to like run the garbage collector here, and the memory usage stays like roughly the same. I deleted the huge cycle. By the way, this is basically running like, this is actually running. I'm just basically running this around, like doing it in a REPL, because again, we create all these like underscores and like don't want to have to deal with it. So the memory usage here is like 493, 250, 264, and I'm going to allocate objects until the garbage collector runs. So here we can see it only took 340 allocations to finally collect that cycle. Now, let's say I start by doing 1,000 allocations, like before we make that object garbage. So this is like pretty similar. So I allocated like 1,000 empty lists, which are going to get tracked. And then I try to delete it. Of course, like it doesn't delete it right away because it's a cycle. And then it turned out that this time I had to actually allocate 2,179 objects. And the reason that this happens is because when an object is unsuccessfully attempted to be collected, it gets put into what's called the next generation. So there's 3 generations. There's generation 0, there's generation 1, generation 2. So my huge cycle got stuck into generation 1, and then it took that many more allocations, essentially 10 times 700. You know, there were other like allocations that took place in between, so it's not exactly 7,000. It's roughly a third, actually, because there's like about 3 times as many. So it took more allocations to get that huge cycle to go away. Now, if I add a bunch of additional allocations in between, then it takes a lot longer. So I'm allocating a lot of objects now and waiting for this memory usage to go down. And this time it took about 77,000. So this is just like, this is what it means to have a generational garbage collector. So Del. So, you know, you might think that I could have done that demo under Del. I'm just going to take questions at the end. So before Python 3.4, objects with user-defined, like under Del methods, weren't actually collected by the cycle detector. Essentially, they said, you know, if you're going to define your own finalizers, then I'm not going to be responsible for collecting your objects in the wrong order. So instead, they create a reference to them and put them into this gc.garbage. This is an array in the garbage collection module. And then if you want to collect them then they want you to like manually untangle the references and then do a collection again. So this is like an example of, you know, with great power, you know, using your own defined finalizers comes great responsibility untangling your cycles. And I'm just going to finish off by quickly touching on a different module. So this is there's a module called weak refs, and so this lets you create weak references. The thing about weak references is that they don't actually increment the reference count. So you can create as many weak references as you want, and the object is still going to get collected when the number of real references goes to 0. And when that object actually does get collected, your weak references might still be around, but each weak reference you define creates a callback, so you can just execute some code. It's kind of like Dunder-Del, except it has a guarantee that Dunder-Del doesn't, as we saw, in that each finalizer is guaranteed to be called only once. So once it gets called once, it's dead. And the weak refs module defines a few container classes that basically have these callbacks where it'll delete the entries when their corresponding objects are garbage collected. So we've got a weak key dictionary, so you can make a dictionary where all the keys are objects, and when those objects are collected, they just magically poof out of your dictionary. So this is great to use if you want to use like a caching layer where you just want to keep track of all the objects that you still have around in memory, or all of your, you know, sockets, or all of your like open files, but you don't want like the creation of this dictionary to prevent the things from being collected early. And just a historical note, when weak refs were first implemented, there was a way that by manipulating the generation number, you could actually like cause a segmentation fault by like pulling a real reference out of the weak reference with the finalizer, and the object would get collected, and then you had a real reference, and you'd be able to dereference it, and it blew up. And this was an actual like real bug in production that blew up Zope. I think that's it. So